Douglas Dunn, who is a professor at McMaster University. So he's in a department computing and software at McMaster University. So he earned his PhD from University of Illinois and Champaign, and undergraduate and master degree at University of Toronto. Among his current interests is how to design, incorporate demand forecast models for use in healthcare systems. He's more generally interested in statistical modeling for resource allocation and management in computing and healthcare system. So, Dr. Dang, the floor is yours.
Great, thank you very much. Let me just uh, sorry. Let me just share my screen here. Uh, okay, so thanks again. So, oops, we're at the. So I just wanted to talk to you a little bit today about where I use AI and machine learning in my research. So this is less about the nuts and bolts of machine learning and more an application where I use it. So I'm interested in one of the things I'm interested in is healthcare applications. And so let me just comment. I was interested to hear the answer, this discussion about what people should study. So Miriam is the student who worked with me on this. And in addition to learning about machine learning and programming, so one of the things that was important in this work was also that she also gained expertise in statistical analysis. So I think in looking at a lot of outputs of machine learning models, statistics are an important thing to learn. So let me just start. I mean, I think a lot of you know this, but what do artificial intelligence and machine learning systems do? It's not a one size fits all. So there's various things they do. Classification. If I look at an image and I want to classify, is this an image of a cat, for example? Let me just highlight a couple others. Generative AI, which I just heard was being talked about, large language models, recommendation systems. You run into these all the time. Computer vision. So there's when we think about artificial intelligence and machine learning, we're not talking about just one thing in some sense. We're talking about various tasks that they do. Now, the bottom one is the one that I'm interested in for this and that's forecasting. So we want to use these techniques to do forecasting. And what I'm particularly interested in is forecasting of demand for blood products. So just to tell you a little bit about these things. So if you go in and donate blood, then these whole blood donations are broken down into various products. So there's not just um, the blood you give, they're broken down into red blood cells, plasma, platelets, and all of these blood components have different uses for people that require bloods. So I'm going to talk today just a little bit about something called platelet products. So platelet products are the part of your blood that promote clotting. So if people have trouble with bleeding problems, so if they've had some kind of accident or trauma, they're bleeding, uh, these platelets can help clotting. But also when people are getting treatments for things like cancer or they have autoimmune diseases, sometimes the treatments for that uh, uh, make people more prone to bleeding. So transfusions of platelets are given for improving that clotting. So a key thing when we're looking at these things is that these platelets cannot be frozen. And so after about 7 days, it varies, these are no longer usable. So, we'd have these platelet products and they couldn't be used. So what's our goal when we're looking at this? So I'm working with hospitals in Hamilton, and the idea is that what we want to do every day is order some units of platelets. So if you see in that picture, those bags are that the lab technician is working with. Those bags with the yellow product in it, the yellowy product, are bags of platelets, so that the hospital has enough to satisfy demand while not keeping too many excess units. So the idea is, each day the blood bank at the hospital says, how many platelets should I order for tomorrow? And we want to figure out how many we need. And we want to have enough for the patients, but we don't want to keep too many, because if we keep too many, first of all, if you see by that picture, they can be a little bit expensive to store. And then we have this issue that if we keep them too long, they're just not going to be good anymore. And one other thing I'll mention is that doctors prefer to use fresher platelets in general. So there's some idea that the fresher these products are, the better the results will be for the patients. So what we want to do is we want to use machine learning here to forecast what the demand will be for the next day. So the idea here is that if we can predict the number of units for the next day, then we could simply order exactly what we need, right? So if I have my machine learning model that said I put in some information and it says tomorrow I need 25 units, we can order 25 units and we're good to go. Now, one thing that happens in hospitals these days is we have lots and lots of data available to help us make such predictions. So we have, in particular here, so sorry. So I have lots of data. I'll talk about that in a minute. But the idea is we want to predict how much we need, and then from there, proceed. So what are the desirable properties of the prediction? So I'm going to build my AI machine learning model to do these predictions. And the first thing, of course, that I want is accuracy. We want the predictions to be as accurate as possible. And one of the things that I think is important when people are looking at these applications is, do we need these predictions to be exactly right? This might not even be possible. Or is there some notion of sufficiently accurate? And I'll talk about that a little bit later. The second thing we would like is for these things to be explainable. So when we build our model, we take this data and we build our AI model that's going to make these predictions. What we would like to know is some insight into how the model is actually making these decisions. Right? So what data is it using and how is it using to make these decisions? So we don't want a so-called black box model. We don't want, in the end, something that just you throw a bunch of data into it and it says, I need 25 tomorrow. The reason why is if you talk to people at the hospitals, they will not implement these models if you can't convince them that it's making its decisions based on reasonable criteria. And I'm saying here, and this I think is not just in the domain that I'm interested in. So certainly people in the hospitals do not trust black box models, and they shouldn't. So when I'm building these, they shouldn't trust black box models. So when I work with the people at the hospital, we work on building models that make sense to the people using them. We also want these things to be lightweight. So the fact is that the people that are using these in the hospital, we don't want them to require a lot of resources. That could be in terms of expertise or computing resources. In particular, we've had some interest in this work from people working in third world countries where they don't have the same resources that we have here in Canada, for example. And we would like these things to be lightweight. I'm not sure. One of the things that's a big thing in the news these days is what is the energy usage of AI systems. So one of the things that the hospitals are concerned about are, this is not just for society, but for their power bills. So how much energy are these systems using? And as I said, there's some low resource users. So I'm mainly going to say a little bit about accuracy and explainability. I'm not going to talk so much about the lightweight part, but these are three of the things that there's others, but these are three things that are really important for these models. And I'll emphasize again, explainability. This is across applications. You might hear people talk about fairness and these kind of things when AI models are making decisions. So we want them to be explainable. So let me just say a little bit about the data that we have available. So when we worked on this project, we had 9 years of data of every patient that came through Hamilton hospitals that used blood units. So a lot of data, something on the order of, I can't remember the number now, but there were something like 60, 70,000 patients that use platelets only. This isn't red blood cells. This is just this particular kind of blood product. So we have data about what they received. We have data about the patients, their age, their gender, their blood type. We have information about where people are in the hospital. So we have um, uh, how many people are in certain parts of the hospital. A big thing we have is that for every patient that's, say, in the hospital, we have the results for all of their tests. Most importantly for us is blood tests. So essentially, there are on the order of a couple of hundred blood tests that can be ordered. And we have that information for all of these patients. Now, not all patients get all tests, so we have some tests for some patients, not for others. We have the past demand, how many platelets were used per day, and the result is hundreds of variables. Okay, so one of the things that's important when we're building these models is something called feature selection. So if you remember, I talked about this goal of explainability. So I want models that are explainable. And one of the things we find in healthcare applications, if we have an AI model that has, say, thousands of inputs, so thousands of different inputs going into this AI model that it's making some decision or prediction about, our goal is to choose a small number of variables that make significant difference in the predicted value. So kind of generated on the side here, these features are different variables. So you might have patients' age, gender, blood test one, blood test two, blood test three. And what we do is we try to reduce the features that are actually used to come up with final features. This does a couple of things. It results in this explainability. So the idea is that now we're only using a smaller uh, number of features. And if we go to somebody at the hospital and say, yes, we're using this small subset of features, and they can look at it and say, yeah, it makes sense that we're using those features to make those decisions. But if we go into the hospital and say, we're using 2,000 variables and making a decision, they're going to say, I don't believe you. I don't believe that we really need all of that data. So we use an approach. I don't think it's important for you listening here. We use an approach called lasso regression. But if you outside of this talk, if you look, feature selection is one of the components of machine learning that's important. So we're taking this large data set with a large number of variables and reducing it to a smaller number. So I don't expect you to read this table, but what I want you to take away from this is we had on the order of, say, 300 variables. We reduced these to 30, and we showed this to people at the hospital, and they said, yeah, this makes sense. And the one thing, sorry, the table's a little bit cut off, but one of the an important feature for us, if you look towards the bottom, is the day of the week. So the demand might depend on the day of the week. In particular, the demand on the weekend is not as high as the as during the weekdays. And as I said, it's explainable. Features like abnormal platelet count. So people have a low number of platelets, they're more likely to need one of these transfusions. And the number of patients in units where bleeding is more likely. So if you can't really see that well, but hematology is where people that have problems with bleeding are located. So This gives feature selection, but what happens with our artificial intelligence and machine learning? It's used to decide how much weight to put on each feature. So I've decided that I want to use these 30 different features, but how much weight should I put on each of these? So I'm not going to go, I'm going to put these names up here. So we did three different prediction models. One is called lasso regression, which we used for feature selection. There's another machine learning model called a random forest, which is kind of a decision model. And then we used, everybody's probably heard of neural networks, but we use a particular kind of neural networks called a long short-term memory. So we took our data, we trained these models, and here's what we came up with. So all three approaches have similar accuracy, and this is the only kind of mathematical thing that I'll put up here. So one of the things that people use to measure accuracy is something called root mean squared error. And so what that does is it takes the difference between the actual value and the predicted value and squares it, and then takes the average of those and takes the square root. The reason why we square it is this means that if I make bad errors, they're amplified even more when I measure this. But there's other ways that people measure things. And this is where the statistics that I mentioned come in. There's various statistical measures of how good my predictions are. And you need to understand the pros and cons of using different statistical measures. Now, these numbers might not mean a lot to people, but what I want you to take away is I use these three different approaches, and those numbers, the error is close to each other. So this is telling me that whatever machine learning approach that I use, I'm getting roughly similar results. The other thing that is that these numbers are not close to zero, right? So they're not close to zero, and that means that my predictions, no matter what I do, my predictions, I'm going to have some error. So one of the things that I want you to take away from this is that when I build a machine learning model, my predictions are going to have some error. So using them as truth is dangerous. So if I take the output of my machine learning model, try to use that as truth, I could run into trouble. It's also not clear that we can build better machine learning models. There is the thought that maybe these kind of errors we can't do that much better, partly because there's inherently just some randomness in this demand. So I just want you to see, here's what our kind of prediction model looks like. So the gray line is the gray solid line is the actual demand in 2018. So this is per day. And the red line is the prediction model that we built. So as you can see, the prediction model is roughly capturing what the demand looks like, but it's not doing very well at capturing spikes, both upward going and downward going. So what does that mean? So that means we have to be careful, right? Because if I look at the spike that's just past the date, this tall spike, if I just ordered my prediction, which is the red value, I'm going to be about 15 to 20 units short. So I need to do something. So I'll just say a few words about this and then stop and try to answer questions if there are any. So we cannot use predictions as truth, in particular shortages would result. So to make sure that we have sufficient, we may need to order extra. And one of our problems is, well, how much extra? And we can develop mathematical models for this. But we found that another approach for artificial intelligence and machine learning can also be used here is an area called reinforcement learning, which, for example, reinforcement learning has become very popular, for example, for training robots how to do tasks. But here, we could train our system how to order these platelets. So these can be used to determine ordering policies. So we're currently doing some work on this reinforcement learning side of things. I have a student right now who's doing a lot of interesting stuff in that area. And I think I'll stop there. So what I hope that did was at least give you an idea of an application where I'm using machine learning and some of the considerations that I use when trying to implement machine learning for this healthcare application. So thank you very much.
Thank you very much, Dr. Dang. We do have quite some questions from the audience. So the first questions we get is that thank you very much for your presentation. So if I want to pursue research that combines medicine and AI, what major should I study? Computer science, biology, or chemistry?
Um, so I think that there is various possibilities depending on where you want your emphasis to be. I think computer science is, computer science. So the student that I've worked with she developed skills in the healthcare side, but now she's working at Toronto Dominion Bank. So if you develop a good uh, basis of skills, I think computer science is a good way to go. But for example, there are areas like biomedical engineering. I know our program at McMaster. There's people are doing a lot of machine learning in the biomedical engineering side of things, but the pure sciences too. I mean, chemistry and biochemistry these days, a lot of drug discovery is so I think it depends on if you want to develop skills that are transferable between different areas, I think that computer science is a way to go, but you can't go wrong. If you're interested in those health applications, going into something like biochemistry, and if you just check the program and see what they have in terms of machine learning content, I think that's a good way to go. And there's also, sorry, I will say also that a number of places have biostatistics programs, and those are also programs that are strong for healthcare and AI.
Thank you very much. So another question the audience have is from your slide, I noticed that your datasets includes hundreds of patients related variables. So really interested in how such medical datasets are cleaned and analyzed before AI model are applied.
Yeah, so it's a excellent question. So cleaning at the moment is uh, we use some kind of sanity check rules. So right now the cleaning is done in because we're doing research, the cleaning was done manually by the students. So we look for things like invalid dates. We look for numbers that are larger than what would be expected. We look for blood test results that don't make any sense. So for most of our variables, we have what the fields should satisfy. There aren't a lot of logical rules because each entry. So sometimes when you do data cleaning, there are things like I work on another application on appointment scheduling, and sometimes there you can look for things like dates being out of order for data cleaning. But right now it's pretty manual. The processing. So the cleaning's just done in an Excel spreadsheet. The pre-processing, there isn't that much pre-processing that we do at this point. So it's too bad Miriam isn't here because Miriam could have answered that question much better than I could. Sorry.
Thank you, Dr. Dang. So another question is, so for high school students like us, so who don't have it was actually the same person as the last question. So
Okay.
for high school students like us, who don't have access to the large scale medical data, what would you recommend we do to start meaningful AI data science projects?
So um, there are some. If you look around and please, my email address is here. You can, if you want to contact me afterwards, do so. There are for various applications, There are some open source data sets that are available that people often use to, one of the things that's important in research is we like to use in a lot of settings similar data sets between researchers because that gives us a common ground to compare results. So for example, uh, I'm doing some work now that is in healthcare, but one of the things we've used to validate our approach is actually using a huge open source data set from Walmart. So Walmart has, for example, a huge open source data set on sales information, product sales information that we've used for doing this kind of demand forecasting. So certainly these medical data sets for ethical reasons aren't, if you asked me for the data set, I couldn't give it to you for ethical reasons. But there are, for data science projects, there are open source data sets out there that are interesting. So if you want to follow up with me, just send me a note and I can give you some pointers.
Thank you very much, Dr. Dang. So another question is about the black box model you mentioned, right? So you mentioned in medical that it's usually not acceptable to have a black box model. So the question is that can black box model more be used in other categories? Like can it be more acceptable in some other domains? For example, would it help on tasks that needs a result quickly? But don't have those too much ethical issues.
So I would say that, so one thing I'll say is that it's not clear to me that black box models are any quicker than these approaches. I have to say that I firmly believe that if somebody presented a black box model to me in any domain, I would have some inherent distrust about that model because there's a phenomenon in machine learning called that when people are building these models called overfitting. So overfitting means that I take the data that I use to train my model and that model matches my data very well, but when I use new data into that model, then the results aren't very good. And the problem is if you have a black box model, it can be difficult to make the conclusion that if I give it a new set of data, that it will still work well on that. Whereas if I have this idea about what variables are being used, then I might have some confidence whether my model generalizes to other settings. So I'm not saying that black box models can't be used, but if you talk to now anybody working in machine learning, is that explainability is a super important property of building a machine learning model.
See. Thank you very much, Dr. Dang. So due to the tight schedule, we will need to move on. So let's just send another some other